So it's our pleasure to have Davide Ruffoni with us this morning. So Davide did his PhD thesis in Berlin with the team of Peter Fratzel. Then he moved to ETH Zurich in the team of Ralf Müller. And since now nearly 10 years, he's the head of the mechanics of biological and bioinspired material in the University of Liège.
Yes, correct. Thanks a lot, Nicholas, for the introduction. Yeah, good morning, everybody, from my side as well. It's really nice to be here in this beautiful hotel, beautiful village, beautiful country, let's say, right? I'm Italian, as you can see. So, and actually, yes, I like maybe to start a little bit presenting where actually we are working. We are working in Liège, which is a city, French part of Belgium. I think I did it wrong here. It's actually below the border between, let's say, Wallonia and Flanders. So we are actually below this river here. Well, Liège is a nice city. Before going there, I just knew the bike race, Liège-Bastogne-Liège. But then when I arrived, I also knew that there are some good beers, actually. There are also good sweets. And this is nice to, let's say, after the race, you can refill. There is also university, of course, University Hospital. Actually, it's the only university in a French-speaking part of Belgium which has a university hospital, and this is quite nice for my research because we can have direct connection with clinics. And last but not least, there is also our research group with these very, let's say, motivated and nice, let's say, students. And I like to present the work that we are doing all together. And we are actually, our research is divided a little bit along two lines. One line is looking at biological materials, and we look at biological materials for two main reasons. Some of biological materials are also clinically relevant tissues, so we are interested since a few years at investigating the bone-tendon interface, and this is something that I will present today. So the attachment of soft tissues to hard tissues through something which is called, let's say, medicine, enthesis. This is a name that we use for this. We are also interested in investigating biological materials because most of them are really high-performance multifunctional tools. So we are interested to understand and, let's say, discover the design principles that nature is let's say, putting in when fabricating those materials, and this is also one example that I'll show today. And in parallel to this, we also try to, let's say, prototype, fabricate, develop what we call bioinspired materials, and we had already a nice introduction yesterday about this bioinspiration principle. So a little bit for us, what we try to do is we first observe a biological material, and also we try to learn, let's say, the constraints that nature is putting on those materials. We then focus on a defined construction principle that we isolate. Typically, this is something at the small length scale, micrometer length scale. And then we try to replicate this construction principle, typically at higher length scales, millimeter or centimeter length scales. We use 3D printing, and then in parallel to this, we do modeling, computer simulation to explore a little bit, to enlarge the parameter space that we can explore, and this is a little bit the way we try to, let's say, prototype those type of materials. A little bit the motivation to do this is just a reminder, because I think you know it very well, that biological materials are somehow, let's say, champions to combine conflicting requirements. So if I take the example of bone and I plot fracture toughness and stiffness, as you well know, these are two requirements that are in conflict. So a material which is very stiff typically is also very brittle. And bones, for example, are composed of a ceramic-based material, calcium phosphate, and a polymer, collagen. And when we combine those two ingredients in bone, well, we always try to make, let's say, to retain the best of the two constituents. And this is something that in engineering materials, we are still not able to do as efficient as in nature. So if you take composite materials in engineering, absolutely speaking, they show typically higher properties than biological materials, but just the relative combination of those properties are not as efficiently done as in biological material. And there are many reasons for this, and one reason is that biological materials are somehow solving conflicting requirements through a hierarchical arrangement of different, let's say, constituents. So typically all biological materials have very intricate hierarchical architectures, and this is what we call actually then architecture materials are all material which features many intermediate length scale between the elementary building block and the macroscopic component sides. And this is also something that we try to introduce in engineering materials, because introducing architecture can, looking just for example at energy, fracture energy, introducing an internal architecture can of course increase significantly the amount of the energy that the material can absorb before fracturing. So this is a little bit the motivation. And now I start to show the first example of today's presentation, which is the attachment of tendon to bone. So tendon and bone are strongly dissimilar tissues. They have very different elastic properties, but also energy absorption before failure, failure strains. And attaching those tissues is very challenging. And somehow this is solved by nature by very specialized interfaces, which I said before they are called enthesis. And typically at those interfaces there is the presence of a third tissue which is different from tendon, is different from bone, and which is called fibrocartilage. And fibrocartilage is a tissue which is not a lot investigated, and this is where we got, let's say, our attention on. And actually, to enter a little bit more in details, there are two types of fibrocartilage. If you consider here, for example, the insertion of Achilles tendon into calcaneus bone, so we are speaking about the ankle joint here. And so there is a dedicated fibrocartilage, which is called enthesis fibrocartilage, which typically has to accommodate the tendon. So the tendon enters in bone here through this tissue, fibrocartilage. And also in this region up here, there is another type of fibrocartilage that now is not attached with the tendon, but somehow needs to protect the bone and the tendon from relative sliding and compressive forces between these two tissues. So these tissues are not well investigated, and we are interested to understand a little bit the properties of this region here. And yes, let's say now to enter a little bit more in details. Well, bone has a Young modulus about 20 gigapascal, tendon, let's say 0.5 gigapascal, and they are connected over a length scale of about 500 micrometers. And this is quite amazing because this region here supports large forces that can be higher than body weight for millions of loading cycles. And this is, of course, we are not the first one to investigate this. Many people have already looked at this. And there are several construction strategies that nature, let's say, is putting in place. For example, we know there are some gradients. Nicola also did a study on this. There are gradients, let's say, in mineral content. Bone is mineralized, tendon is not mineralized. At the interface, there are gradients in mineral content, gradients a little bit in the organization of collagen fibers. And what is interesting is that there seems to be a region which has even lower elastic modulus than tendon, and of course lower than bone. So the attachment of bone to tendon goes through a region which as even, let's say, is even more compliant than tendon itself. So this is something that people have reported already. Then what is also quite interesting is that those tissues are fibrous tissues, and what people have discovered is that tendon fibers, which are depicted here in purple, before attaching to bone, they, let's say, splay out to increase the attachment area, and they also unravel in smaller fibrils, what we call smaller fibrils. So this is something that has been investigated. And last but not least, those interfaces between tendon and fibrocartilage and between fibrocartilage and bone are not flat, but highly rough and highly interdigitated. And this is also something that Kanten, my student, will show you today, I think, in some minutes, not some minutes, half an hour or something like this. So most of these, let's say, state of the art is concentrated on looking at things from the tendon side. So people have investigated a lot what is happening when we go from tendon to bone, but not so much when we go from bone to tendon, let's say. Is it not known if bone also shows some structural mechanical adaptation when approaching the interface with tendon? So most of the research has been looking at the tendon side. And One other thing that we are interested in is more, let's say, the biological aspect of those two tissues. What we know is that bone is rich in cells which are somehow buried inside the highly mineralized tissue, and they form a highly interconnected network which is called osteocyte lacunocanalicular network. So this network allows communications between cells, and it allows also bone somehow to measure the local strain. The same is true in tendon. So tendon, we have tenocytes. They also, it seems that they are also forming a very interconnected network, and what we do not know if those two biological networks communicate through the interface. This is something which is still not known, and this is something that we are interested in, and we want to look at this. So basically what I will present is an investigation, multimodal, let's say. We use different techniques to investigate the tissue microporosity. So these are tissues which contains a lot of pores, and we want to understand a little bit if those pores are oriented, and if yes, why they are oriented. Then we want to investigate a little bit the composition, mineral composition, and the organization of the mineral fibers, and biomechanical properties. And typically we investigate local biomechanical properties based on non-indentation. And then last aspect that we investigated is this crosstalk between bone and tendon cells or cartilage cells. Well, in terms of microporosity, what we did some microcomputed tomography, so X-ray analysis, high resolution X-ray analysis, and we focused first of all on this region which is where we see this periosteal fibrocartilage. So this was the fibrocartilage which has to accommodate sliding between the two tissues. And what we saw is that there are some pores to accommodate the blood vessels, and also some other pores to accommodate cells. So these are once again pores inside the highly mineralized matrix. And if we investigate a little bit the distribution of those pores, the anisotropy of those pores, the orientation, we see no preferential orientation here. So it's an isotropic porosity, so to say. And when we do the same exercise down here where the tendon is inserting, we see very aligned structure. So these are the same bone, two locations which are very close to each other, but which are solving different mechanical function, and this is somehow reflecting in the microscale porosities, because we see, for example, fibrocartilage cells which are well aligned, and also blood vessels in this region which are highly aligned. So somehow there is the fact that tendon is inserting in bone is reflected also in the bone structure hundreds of micrometers away from the insertion point. So the tendon is able, or let's put it like this, bone is able to respond to the mechanical requirement imposed by the tendon by aligning its microstructure. So we see some preferential orientation here which matches the insertion direction of the tendon. Then we look at the mineral content, so how mineral is distributed in bone. These are 2D maps, high resolution maps, quantitative maps of mineral content that we measured with the backscattering electron. So this is the tendon, not mineralized, and this is the bone. So what we see is that, first of all, there is a line appearing very red here, which we call cement line, and this very red line means high mineral content, and this is a kind of glue interface which is gluing fibrocartilage to bone. So this is there are specific compositional modifications to glue these two tissues together, and also we see that here there are fingers of fibrocartilage penetrating very deep in bone. So it's an interface which, as I said before, is highly interdigitating. And so this is, let's say, to increase the anchoring properties like tree roots, if you want to see this. And to some extent, this is also true in fibrocartilage, but less. So due to the higher forces which are transmitted here at the tendon insertion, we see that fibrocartilage tissue is anchoring very deep in bone to actually anchor the tendon also. And that's basically it. I think this I skip. Now, you remember in the introduction I said that people have concentrated at looking what is happening more from the tendon side. So there is this beautiful work that analyzed fibers of tendon when reaching into bone. And what we did now, we visualized fibers, orientation of fibers inside bone. So for doing this, we use a technique which is called second harmonic generation microscopy. So we excite bone with a laser light, and we look at the second harmonics which are coming out from the tissue. And what we see actually is is that at the interface, so let's say where tendon is inserting into bone, here is tendon and here is fibrocartilage, we see that what we call the second harmonic signal is very uniform, very strong, and this suggests very aligned. Whereas if we look, for example, up here where there is no tendon, we see a much more heterogeneous signal, and what you see here in this picture are the orientation of the tendon mineral fibers, which are much more, let's say, anisotropic than what we see at the insertion. And another thing that I like to highlight is that from, let's say, fibrocartilage side, fibers tends to arrive more perpendicular at the interface with bone, and from bone side, fibers run more parallel to this interface. So there is some kind of change in fibers orientation at the interface between fibrocartilage and bone, which is not present when tendon is inserting. So this is how we are, let's say, investigating those aspects. Then we did some non-indentation. So we did several, let's say, grids, and with non-indentation we measure the local elastic properties of the tissue. And what we see is that enthesis fibrocartilage, which is the fibrocartilage attaching tendon to bone, is much more homogeneously, mechanical homogeneous. So these are frequency distribution of the Young modulus that we measure in bone, in periosteal fibrocartilage, and in enthesis fibrocartilage. So at the attachment side, we see much more homogeneous mechanical properties, which somehow reflects the fact that fibers are also much more organized and oriented. So this is now, well, this I think I can skip. Then we also try to connect, let's say, how is the, let's say, the Young modulus, are there gradients at the interface when we go from tendon to bone? And are there, so let's put it like this, the common understanding is that the interface between tendon and bone is graded in mineral content and is graded in mechanical behavior. And we want to see if we also see this in our system, and if we see differences when we compare the interface between unmineralized tissue and bone up here and down here where the tendon is inserting. So if we are doing this up here where there is no tendon, this is when we go from unmineralized tissue to bone, and we see a gradual transition in calcium mineral content, and we see that the Young modulus also follows quite nicely this gradual transition. So we can see a graded material. What is interesting that when we do the same measurement at the enthesis where the tendon is inserting, we basically see no gradient in mineral content. So we see that all the mineral is already, all the bone is already fully mineralized. And this is reflected in, let's say, a Young modulus, tissue modulus, which is also already very, let's say, it reaches already 20 gigapascal, which is the maximum that we observed there. So we do not really see a lot of gradients here, which was a little bit unexpected, but we see that, let's say, all the tissue is highly oriented, highly stiff, and ready to take the load coming from the tendon, and we assume this is something which is done to increase the strength of the interface, so to really align all the fibers to take up the load from the tendon. And last point is a little bit this communication between the two types of cells. So these are samples which got some stain. So we stain the samples with rhodamine, which is a small molecule which could diffuse inside all the porosities present in the bone. And then with laser microscopy, we excite this molecule and we can see what is happening. Can I replay maybe the video? So this is we are scanning through the cross section. This is fibrocartilage and this is bone. And what you see is that there are some regions in fibrocartilage that get colored, let's say. So this means that our staining agent could diffuse from bone to fibrocartilage. And the only way to diffuse is through some pores, because those are highly mineralized tissues. So there is no diffusion in that sense inside the tissue. They can only, the staining can only travel through the pores. And when we look a little bit in details, what we see is that here are bone cells, osteocytes. These are the canals of those cells which connect to a blood vessel, and we see a blood vessel which crosses from bone to fibrocartilage and then brings the information to the fibrocartilage cells. So this are proofs that there is indeed some communication between bone cells and fibrocartilage cells. And this is very interesting in terms of mechanobiology, because these are two tissues which can respond to mechanical forces. And if they can communicate with each other, they can exchange information with each other, and they can, let's say, modify in response to mechanical forces. And what is interesting is that we see much less communication at the periosteal side. So we see a lot of communication at the insertion side, where tendon is inserting, which is a very critical location in terms of mechanical requirement. And so we see a lot of exchange between tendon cells, between fibrocartilage cells and bone cells, and we don't see a lot of exchange at the periosteal side. So there is a kind of barrier where bone cells, which are here in the, which color is this? I don't know, greenish kind of. And here we see really few cells which got stained. So there is something like interesting difference between these two tissues. Yes, so sorry, I'm going a little bit fast, but this was our, let's say, state-of-the-art work on these interfaces between the two tissues. And now I like to show one other small example of a biological material which is considered a high-performance multifunctional material. So there are actually, this is a collaboration that we are doing with the biology department. There are these stomatopoda or mantis shrimp. They are crustacean living at the, let's say, in the sea, and they are known for their very aggressive behavior. And I don't know if you recall the keynote of yesterday, spoke quickly about nacre, which is considered a highly impressive biological material. And these guys actually are able to destroy nacre. So they have this hammer-like appendage which they can deploy very fast. Actually, this is the fastest accelerating object in nature. It can reach speeds of 20 meters per second and can destroy this nacre layer, the shells. This has been investigated a lot. This is now investigated because it's high damage tolerance that can destroy nacre, which is actually composed of similar constituents, chemical elements, but just the organization is very different. And there is a second group of those animals which are less investigating, which are called spearing mantis shrimp, and they're also quite interesting because what they do, they live actually hidden in the sand, and when a fish swims close by, they can impale the fish, let's say, with this also very rapid movement. I hope that the video will work. Let me see if it's working, not working. This is a pity because it's working. Poof! So they're capturing the fish also with a very fast movement, 10 meters per second, and voila. So this is now, this let's say frontal appendage is composed of many harpoons, and the structure-function relationship of those harpoons is not well investigated, and this is what we want to understand a little bit more. If you think a little bit about mechanical requirement, these objects here, they have to combine high toughness because they have to sustain the initial impact with the moving fish, with the skin of the fish, and they also have to combine high stiffness to allow sufficient penetration in the fish skin, right? And all of this has to be coupled with strategies to retain the fish and to take him inside the cave, let's say. So these are very, let's say, thin and elongated structural objects. So we know from mechanics that these can be, let's say, weak, right? They can be weak, and we want to understand which are the reinforcement strategies that nature put in place to have these efficient biological harpoons. So already one thing that we observe, if we look at this with micro-CT once again and electron microscopy, we observe serrations. So on the surface of these harpoons there are serrations which are of course very effective with to interlock with the tissue of the victim and to retain the victim. And also what we observe is that this is now a cross-section of this spike. We call this a spike. This is a cross-section, and we observe this is actually a multi-layer system. It is composed of 4 different layers. In the inside here we see fibers. So all biological materials are based on fibers. So here we see fibers of chitin, which is a biopolymer, which form this so-called Bulligan structure. And then in the middle layer, what we call striated region, we see that fibers are all parallel with each other, and in this picture here they will come out of the screen. So this is already a strategy to reinforce longitudinally the spike, because we see a lot of fibers running longitudinally. And what surprised us quite a lot is that there is a small layer here, you can see a bit, which is composed once again of a Bulligan structure, much thinner Bulligan structure, and then there is the outer layer which is highly mineralized. It's white here, so this means high mineral content, which has no fibers. So this is one first finding. Okay, it's a multi-layer material. In terms of element composition, this is not so surprising. Of course, what you should know for biological material is that they mainly use very simple chemical elements in contrast to engineering materials, and here we see only calcium, phosphorus, carbon, for example, as major elements. And we see that in the outer layer, highly mineralized layer, there is high presence of phosphorus and of calcium. Then there is a drop corresponding to this Bulligan interface, and then, okay, then it's not so interesting. And if we look with the Raman microspectroscopy, so this is, we exploited the Raman effect to see a little bit the mineral phases. So things that appears homogeneous under electron microscopy, energy dispersive X-ray mapping, so things that appears homogeneous in terms of chemical composition, they are not homogeneous in terms of mineral phases. And actually we see 3 mineral phases reinforcing this structure. So we see fluoroapatite, which is a crystalline mineral. We see amorphous calcium phosphate and amorphous calcium carbonate. These 2 guys are common. Fluoroapatite is unusual, and fluoroapatite is harder and is also less water soluble than the other 2 minerals. So this is already a modification which is happening here at the surface to make this impact resistance. Then we did some nano-indentation when moving in a transverse cross section, when moving from the outer highly mineralized layer to the inside, and we see, okay, in the outer the tissue is very stiff, is very hard. In the inside is less, and once again we saw this drop in properties corresponding to the interface between the highly mineralized tissue and the inside, which recalled a little bit what we see in the tendon bone attachment. So there are 2 regions which quite dissimilar properties, which are joined by even a more compliant interface, and I think this was the first observation that was done in this respect. So we then went a little bit higher resolution nano-indentation. By decreasing the space between the indents, we could characterize a little bit better what is happening between the highly mineralized layer, very stiff, the inside layer, and we see this region with lower mechanical properties. And then what we also did, we did some indentation-based fracture study. So the idea is to fracture the tissue locally with high load indentation and to observe the cracks with electron microscopy. And what you see is that if we, this is the indent, fingerprint, and these are cracks, and this is the highly mineralized region, and what you see is that cracks are mainly propagating in the highly mineralized region, but they are not able to cross the interface where we observe this drop in mechanical properties. So all the cracks that we generated do not propagate through the interface. And also here, these are cracks which are generated, let me just, inside the tissue here. And when they are generated here, they tend to go toward the towards the outside, but they are stopped by these thin, less mineralized and more compliant layers. So we assume that this layer, one of the functions of this layer is to avoid that cracks can propagate between the 2 adjacent layers. And what we also did at the end, we tried to see if this system can work also in a kind of, let's say, synthetic system. So we designed a specimen composed of a outer stiff layer, mimicking the outer mineralized shell, and of with 2 different designs. In this region here, we designed parallel fibers, parallel stiff fibers, so they're coming out of the screen, and they are embedded in a software matrix. And then we did some, let's say, very simple 3-point bending test to see how, let's say, an initial notch then how damage that starts from an initial notch propagates. And what we see is that damage propagates very straight as expected, because there are all parallel fibers, so there are no crack stopping mechanism. And when it reaches the hard tissue here, or the hard material, the sample just exploded, let's say, and splashed away from the machine. And in the second design configuration, we added a plywood. So we added a little bit this thin interfacial layer with fibers arranged according to a plywood, so with different organization. And what we see is actually this is quite efficient in interacting with damage. So as soon as the damage starting from the notch interact and reach the plywood, we see some delamination, which dissipates quite some energy, and we see also that further propagation of the damage again dissipates quite some energy. And macroscopically, the load displacement curves are quite different, and when we insert the plywood, we see that we can absorb, if you want, a little bit more energy before breaking the system. Yes, so I guess now it's half an hour, right, that I'm speaking. So I still have 20 minutes. Can I still bother you for 20 more minutes? And now I like to discuss a little bit the second research line that we have, which is more in bioinspired materials. So, and actually this last example is bridging and bringing me already to more bioinspired materials. So the basic idea is that we are using multi-material 3D printing. We use Polyjet printing. So this is a polymer-based approach where we deposited photopolymer inks, which are then cured by UV light, and is a layer-by-layer technique. So this is simple. It's nothing, let's say, too spectacular. But what is nice with this technique is that we can fabricate and we can, let's say, tune locally microstructure and mechanical properties to fabricate what we call voxelated soft hard matter. So we can obtain centimeter size object with a programmable composition and structure at the micrometer length scale. So this is a little bit the general idea why we got quite interested in this technique. So this technique can print let's say, structure with voxels, which have dimension from 20 to 40 micrometer, and which have very dissimilar mechanical character. So we can have soft voxel, rubbery kind of voxel, 1 megapascal tangent modulus, and glassy voxel up to 2-3 gigapascal stiffness, and we can combine these, in infinite types of arrangement. But first of all, before doing and before starting to work with this technique, we got interested in the interfaces between different materials, because you can imagine if you have different materials, there are interfaces between those materials, and we are interested in the properties of those interfaces. And actually, to make it very simple, there are two types. As a function of how you are printing your objects, there are two types of interfaces. So if you are depositing simultaneously, let's say, stiff voxel in gray, light gray, and soft voxel, which are dark gray here, and you deposit them simultaneously before curing the system with UV light, the interface is formed actually before UV curing. So the two materials, they become in contact with each other before curing the system. And otherwise, if you would print the object like this, oriented vertically, so to say, you are depositing the second material in a surface on a structure which is at least already partially cured. And so this we call interface between the two voxels is formed after at least partial UV curing. And we are interested a little bit in the properties. The research question here is, are there different properties? Is the interface different when we have this different situation? And what are the properties of the interface in this situation? And more in general, if I have very simple composite material of soft and stiff voxel, what is the role of the interface in the mechanical behavior of those composites? So very simple composite. So to answer the first question, what we did non-indentation, and we measure the transition, let's say, in reduced modulus, elastic modulus, when going from stiff region to soft voxel, from stiff voxel to soft voxel, for, let's say, when the interface was formed after UV curing, and what you see is a very sharp transition. Within less than 20 micrometer, you have a transition between the stiff voxel and the soft voxel, and these dimensions are comparable to the voxel size, okay? The manufacturer of the printer is declared, the nominal voxel size. Whereas if you go now, if you indent in an object where the interfaces were formed before UV curing, so we design a system like this, having a stiff voxel, soft voxel, stiff voxel, and then we indent it, and what you see is a much broader interface transition, up to 150 micrometer, which is much larger than the nominal voxel dimension. So this means, as you may expect, that if you are, let's say, if the two voxels are deposited before curing, there is chance of interdiffusion of the of the molecular, or let's say, of the constituents, and so they form what we call a more blurred interface. Now the question is, knowing that we have these two types of interfaces, I mean, is there a strong impact on the mechanical behavior when we design composite? So for that, what we did very simple design where we staked different layers, let's say on the top of each other, or let's say parallel to each other, as in this configuration, and we printed this plate-like system to have the interfaces between stiff and soft component sharp, so formed after curing, 20 micrometer, or blurred, formed during curing, and so 150 micrometer. And then we investigated the mechanical behavior of this very simple system, actually, with the DMA. So we explored the mechanical properties by scanning the temperatures from minus 550 to 80 degrees to get the transition temperatures of the two components, actually. And we focus a little bit on storage modulus and tan delta to see what was happening. So in a very simple tensile configuration, when we are building materials, this is white is stiff and black is soft. We do now DMA in tension, and the first thing that we observed is that, well, we scan the same sample several times at small displacement, and we observed that the fourth scan are not highly reproducible. So this is something that we observe both in, let's say, the storage modulus and in the transition temperature. And after the second scan of the same sample, we increase the reproducibility. So this is a little bit a message that after the 3D printing, even though the company says that the polymer have been cured completely, this is not actually the same. So it's not actually the case. So the polymers are not completely cured, and if you, this is a little bit a guideline, is a side comment for those techniques. If you do a thermal treatment after printing up to 80 degrees, you will then reduce a lot the variability of your test. So this is something that we were a little bit surprised. Then we consider sample of very different layers, so 8 layers, 16 layers, 32 layers, and in this case, if we have a blurred interface and we have 32 layers, this is basically only a material composed of interface material. And when we do our dynamic analysis, and you see, for example, here the behavior of the pure stiff component, this is the behavior of the pure soft component, and also in the transition temperature, in the tan delta, what you see is that when you have interface, when you have a blending of the two materials, the interface behavior is very close to the behavior of the stiff component. So, in other words, we say that the interface, or better interface, which is forming when you're mixing the two voxels, is dominated by the stiff component, and actually the viscoelastic dissipation are completely suppressed. As you can see here, the soft component shows this viscoelastic dissipation. This is peak in tan delta at 0 degree, which is completely suppressed when you mix it with the stiff component. So this was already one, let's say, the two main findings so far. And then the last thing that I'd like to show is, let's say, the non-trivial behavior of multi-layer composite with these different types of interfaces. So what you see here is now the behavior of plates like this. So very simple, it's even too simple probably to show it here, because from a mechanical point of view, this is a behavior of a multi-layer system with soft and stiff layer stacked along this direction in 3-point bending. So it's a trivial system. And here is how it behaves when the interface between the different layers is blurred. So is this 150 micrometer in thickness. So what you see here is, let's say, the storage modulus as a function of the different layers. Here is a system of 2 layers, so stiff and soft, 4 layer, stiff, soft, 6 layer, 8 layers, and so on. So by increasing the number of layers, of course, you are redistributing the stiff material away from the neutral axis, and so you see an increase in stiffness, which was nice. Increase in storage modulus is the stiffness, let's say, which was nice, as expected, also in line with beam theory, if you want. Very simple. Exactly the same system, if now the interface between the layer is sharp, actually you see that increasing the number of layers, the storage modulus stays the same. So we said, ooh, what is going on here? Why is staying the same? Why we don't see the increase that is, you know, expected by beam theory? Well, then, of course, we look a little bit in more details into this. We did some finite element analysis, assuming 2 types of interfaces, very sharp, very blurred interface. And what actually we see is that the prediction of finite element analysis were in agreement with the experiments. And of course, if you think about this, it makes sense, because if you have, if the interface is very sharp, or imagine if there is no interface, of course, the behavior of this is dominated by shear deformation, because the soft material is actually decoupling the stiff layer. So the bending forces are not transmitted, let's say. The forces that you apply are not transmitted. And if you have a blurred interface, knowing that this blurred interface has properties more similar to the stiff material, well, it allows a higher stress transmission between the layers, and of course it allows to be more in line with the prediction of beam theory. So this is what was our, let's say, study to characterize interfaces. And then I like maybe to show this study that we did on helicoidal biocomposite. So as I also showed before, fibers are ubiquitous in biological material, and actually fibers are very often arranged as spirals in biological material. So this is an example of cortical bone. In our bones we have fibers of collagen which are spirally arranged, and also in wood, in the wood cell wall, which is the main load-bearing part of wood material, you have fibers of cellulose which are spirally arranged. And having helicoidal, so following this helicoidal construction principle is actually very versatile, because you can tune a lot the mechanical behavior without changing the chemistry of the material, but just by changing, of course, the arrangement of the fiber. And very often we see that in biological composite, they are multi-layer with fibers arranged with different angles in the different layers. And so this is a system which was very interesting for us. And when we look a little bit more in details on a wood cell, so this is, you have to think about wood cells as long cylindrical tubes, which are, let's say, in hardwood, they are empty, and in the wall of this tube you have cellulose which are actually resisting and taking up the load, the weight of the tree. And these cellulose walls are multi-layer, composed actually of 3 different layers, concentric layers. The so-called S2 layer is the secondary wall, is the dominant layer in thickness. This is a cross-section of the wood cell. This is S3 layer, S2 is the thickest, and then S1 layer is very thin. And actually what we know is that thanks to the fiber arrangement in the S2 layer, wood is tuning its mechanical behavior. And the analogy is actually with an elastic spring. You can think a little bit about the wood cell wall as this elongated tube, where you have cellulose fibrils, let's say, which are wounded with a spiral angle. And if this angle is small, the wood tissue is very stiff, so the Young modulus is very high. And if the angle is increasing, this actually is more as an elastic spring and is more compliant. And on the other side, the fracture strain have an opposite behavior. For very small angle, fracture strain are small because cellulose molecules are brittle. And if you increase the angle, wood can reach higher fracture strain. And so there is a tuning, let's say, of the material behavior just by tuning this microfibril angle. And so we were interested to somehow reproduce this principle in synthetic materials. And the first question is, can we print fibers with this technique? And can we print fibers which shows then composite based on fibers, which shows a programmable mechanical behavior. And then can we investigate a little bit the interplay of reinforcing a main layer with thick fibers with, let's say, smaller layers with very thin fibers which are arranged either horizontally or so vertically or horizontally. Can we investigate this system under the idea to work with a system which is still simple but not trivial? It's a very simple system because it's only a 3-layer system, and in engineering now you see much more, multi-layer in that sense, but still is not trivial enough and shows a behavior that can be, let's say, a bit surprising. So the main idea here is to consider once again a 3-layer system with fibers oriented at 0 degree vertical, 15 degrees, 30 degrees or 45 degrees. This is the main layer, and then to reinforce this main layer with either horizontal, what we call fibrils because they are smaller, on the outside, on the inside, or on both layers and on both regions, and also vertical on the internal, external, or both. And the first thing that we did was to investigate if with the 3D printer we could print fibers and what are the minimum diameter of fibers that we can print. So we tried to print from 250 micron up to 1 millimeter in diameter, and then we did some optical microscopy and calculate a little bit the error between the nominal diameter and the real diameter that we would expect. And based on this study, we could say that we could print the smallest fibril that we can print as a diameter of about 750 micrometer with this technique. And based on this, we rescale all our system. So we printed actually 2 types of length scale. We print small fibrils and bigger fibers. Fibers are in the main layer and fibrils are on the reinforcing layer that we call here. Then we 3D printed those structures that look a little bit like this. And we used a stiff polymer for the fibers and a soft polymer for the matrix. Actually, we used 2 types of matrix. A soft matrix where the elastic contrast between fibers and matrix was 500, and an ultra soft matrix where the elastic contrast was more than 1000. And investigated a little bit the mechanical behavior of this in terms of, with a compression test. Yes. At the same time, we did also some finite element analysis of the same system to learn a little bit the way they deform and the energy which is absorbed in the system, replicating a little bit the boundary condition that we had in the experiment. So these are now the first results that we have. So this is how the stiffness of our, let's say, synthetic cylinders are tuned by changing the fiber winding angle of the main layer. 0 degrees, very stiff, and then 15 degrees, 45 degrees, of course, they get more compliant. This is not a big surprise. And this is the behavior with the soft matrix or ultra soft matrix. This is also how the energy absorption is changing for stiff cylinder. Of course, they are very, let's say, weak in terms of energy absorption because they fail by buckling because they have straight fibers, and as soon as I introduce some winding angle, I escape this buckling failure and I can absorb more energy before failing, let's say. And we did some FE simulation which were quite well in line with the experiments. And okay, this I think I skip because it's not so interesting. And what we see also in terms of mechanical behavior, thanks to finite element analysis, is the following. So see the ratio of those systems, so the lateral expansion when we apply a compression, what we see is the following. Let me just see here. So if we have a system with no fibers, sorry, I missed to put the legend here. So this gray here is the system with no reinforcement, so it's just the simple cylinder. And what we see is that by increasing the winding angle of the fiber, the system expands more laterally when we compress it, okay? This is what we see here. And if we add vertical reinforcement, this does not change. But of course, if you would add horizontal rings, horizontal reinforcement, you are basically blocking this expansion. So this is intuitively, you say, and here we quantify this a little bit. But at the same time, when you are blocking the lateral expansion, you are more increasing the rotation of the system. Okay, this is something that we had some insight on the behavior. And then we did the compression test, and these are the last results that I'd like to present. So this is how the system fails when the main fibers are oriented vertically. So this is a typical buckling failure that you would recognize here. And what is happening when we add vertical reinforcement or horizontal reinforcement? Well, things do not change so much. The system, you know, is still failing by buckling. It gets a little bit more higher peak stresses, but the same failure strain is observed. Things becomes completely different if you now introduce some winding angle in the main layer. This is now results for 55 degrees orientation of the main fibers. Now I introduce small vertical reinforcement. Well, it changes a little bit, but you still have this collective buckling of the vertical reinforcement. I'm not sure if you can see here. So these tilted are the main fibers, and here what you see straight are the small reinforcement that we have inserted, and you see they all buckle collectively, and so the system does not change so much its overall behavior. But when you introduce horizontal reinforcement, then you are really able to increase significantly the peak stresses and, if you want, the energy which is absorbed in this failure process. And what you see is this is a typical fracture that we observe in the system without horizontal reinforcement. So fracture in the matrix between the fibers, and here are fractures that we see in the system when we add circular reinforcement, and you see that the fracture is also moving from, let's say, tilted direction to more horizontal direction. So this moving, the way it breaks dissipates a lot of energy, and so we have 150% increase in the absorbed energy before a failure. Yes, I think I'm done almost. Maybe I just show you a very quick things. Since we had also a lot of cellular structure, I also did some work in that respect. And the basic idea is to exploit a little bit, you know, the difference between positive and negative Poisson ratio material. As you know, negative Poisson ratio material are quite unusual material, but they are quite nice because they are supposed to have high impact resistance properties, and they also have non-trivial deformation mechanism. And our idea was to somehow exploit negative and positive Poisson ratio material in lattices to build up a lattice which is composed of, let's say, negative Poisson ratio inclusion in a otherwise positive Poisson ratio lattice, and to exploit a little bit the difference in the deformation mode between these two unit cells to stiffen the material. So the basic idea is, first of all, to investigate the effect of a single negative Poisson ratio inclusion in a positive Poisson ratio lattice, and then to use a pattern of inclusion to reinforce this. So we investigated system like this, where you have a hexagonal honeycomb, where we change just one single joint to have it as negative Poisson ratio, reentrant if you want. And then we did some finite element analysis, and we saw that if you apply a vertical compression on this honeycomb, this large honeycomb, let's say, the region which only one node which shows this negative Poisson ratio is behaving a little bit more stiff, because its deformation along the applied load is less than the regular case. And if you look at the lateral deformation, it's negative. So this means that just a single auxetic inclusion in an overall positive Poisson ratio lattice is able to retain its behavior, let's say. And this was already a little bit interesting to say, okay, just by this perturbing this geometry, I can retain the negative Poisson ratio behavior. And then the idea is now to introduce a pattern of inclusions and to see the behavior of this lattice, both with simulation and with the experiments. And we see that with respect to a positive Poisson ratio, by inserting this auxetic pattern, we have an increase in stiffness of 300%. And I stress this is exactly at the same relative density. So I'm not adding more material here. This is exactly the same material, but just by exploiting this contrast in Poisson ratio, we can increase the overall stiffness of the lattice. And that's basically it. So we show a little bit these two research lines on biological materials and on architecture materials. I think there is no need that I summarize what we said. And I'd just like to acknowledge my co-authors and also our founding in Belgium. And thanks for supporting 1 hour of presentation. Yes.